Hey, hello everyone. In this video, we'll be talking about attention. Ignore this phone. This is my mic for this video. In this video, we'll be talking about attention. Attention. We'll see how can we implement it in PyTorch. So I have been studying about transformers, as you might know already by watching my other videos. So in this video, we'll particularly talk only about attention. Cool. Let's jump right in. Okay, so the attention layer occurs in three places in this transformer. This is the first place here, here in the encoder, and twice in the decoder. So we'll implement one single class. Let me show in PyTorch one single class like this called multi-head implementation, and then we'll use this class for all three of them. All three of them are not exactly the same. They have subtle differences. As you can see, this is called multi-head attention. This is called masked multi-head attention. And this is multi-head attention, but you see the inputs are coming from encoder as well. So this is basically cross attention. Cross attention. Okay. This is plain vanilla. We'll focus on all of them. Cool. Uh, let's jump. Let's see how to implement it. So we know the formula for attention from the paper. The paper states that attention is calculated like this. This is the formula which paper gives us for attention. Given that query, key and value vector, this is how we calculate attention scores. This is what we'll do. And once we have attention scores, what we do is this is how we get the final by concatenating, and I'll touch more on this. So let's look sequentially. What are we going to do? Step 1 in attention calculation is we need to compute Q, K, and V. Okay. So Q, K, and V are basically query vector, key vector, and value vector. Every token or every embedding has its own query, key, and value vector, right? If you are not very clear about this, watch my previous video in which I explain what attention is and how do we, what is the intuition behind it. Okay, so the only point to note Q, K, and V, the only point to note about is that if you look at attention in the transformer, uh, in the encoder, in this self attention, all these three Q, K, and V vectors are derived as linear projections of this input, this one single input, which we'll call X. So all these three are derived from X by multiplying by different parameters. If three parameters WQ, WK, and WV, we multiply with X and we get Q, K, and V. I'll show it. Uh, Same happens here also. The X comes in, and then we calculate Q, K, and V. Here things are a little bit different. If you see in cross attention takes two inputs from previous decoder. Let's call it Y for now, and from let's call it X for now. Let's call it X. What comes from previous decoder, and Y comes from encoder. Right, that is what happens in the cross attention. So how do we calculate Q, K, and V in this respect? What we do is, in cross attention, we derive K and V from the encoder's output. Right? This output, what is going from here, we derive Q and K from this. K and V from this, sorry, K and V. Q is derived from the decoder. Why? The intuition. So what I'll tell you is, basically, let's say you're trying to translate from uh, let's say you're trying to translate from English to French. Okay, this is the English word, the agreement on European, this is French. Right, so source is English, target is French, and we get Q from target. Right. So when I'm trying to understand, when I'm trying to predict, when I'm trying to refine the embeddings, so if you look in encoder, what is happening inside encoder? Here we input the target embeddings. So for example, if I'm trying to convert English to French, I'll input English here, and I'll input French here. French is my target. So in this, what is happening is inside Pura, this French embeddings of French words are being refined, right? So basically, when I want to refine an embedding, what I do is look at I look at other tokens in the same sentence. So self attention here, I will look at other French tokens here in this layer. But in this layer, I will look at other English tokens. Like from target, I look into source. Okay, what are the English tokens and how am I how do I relate to those tokens? This is how it will look. Let's see, on will attend to this uh, this word, whatever this word is. European will attend to this word in French. Area will attend to this word in area is attending to zone in French. So that is what happens here, right? So Q, K, and V. Now we know how to calculate Q, K, and V. So let's just try to see how it looks in code. This is the layer which I'm implementing. Any layer in PyTorch, if I'm implementing, it should extend from an module. I'll come here. So first task is to calculate the Q, K, and V vectors. We'll calculate Q, K, and V vectors. To calculate Q, K, and V vectors, we need linear layers. As I said, we multiply it by, as I said already, we how to calculate is multiply it by the parameters. So linear layer takes care of that. Uh, just calculate Q. This nomenclature is a little confusing. So the input to this layer is not query key and value. These are query key and value. This is basically just in case of encoder attention, all these values just correspond to the previous encoder's output. In case of decoder self attention, decoder has two attention, self attention and where is the paper? Decoder is two attention, self attention and then cross attention. In decoder self attention also, all these values corresponds to the output of previous decoder. In cross attention, query corresponds to the value of previous decoder and key and value corresponds to the encoder output. I can show it to you also. Let me go to decoder. This is the decoder code. In decoder, if we look at self attention layer, we are calling it queries x, keys x, values x, previous decoder's output, as I said. And in cross attention layer, query is from previous decoder, key and value is basically encoder output. So this is nomenclature is very confusing. The paper has introduced nomenclature. These are actually not query key and value vector. You can assume that these are source of query key and value vectors. And once we have these values, out of them we calculate Q, K, and V. Okay, this is something which I have talked about detail in my blog. So paper says like this. This is what paper says. V, K, and Q goes inside. We do linear transformations and then we do our calculations. I say this should be like this. Let's say in cross attention, X, X, and Y goes. From X we derive V. Then from X we also derive K. From Y we derive Q. Y is nothing but previous. Y is nothing but previous decoder's output. And then we do our own calculations. So paper also says like this. Key to what we do is to get query we multiply q with wi, then k with wi, then v with wi. No, we multiply y with wq. Y is previous decoder's output. Then we multiply x with wk. We multiply x with wv to get v and q. In case of encoder, in case of self attention, y is always equal to x. Okay, that is just a little clarification I wanted to make. Now moving forward, once we have calculated in code Q, K, and this. Next step is to split it. Right? Let's see what the next step is. Next step is we will split Q, K, and V into smaller pieces. Why? Because multi-head attention. Our layer is multi-head. So we'll split Q, K, and V into H equal parts. The length of the subsequent parts will be dk, right? So obviously H into dk will be d model, where d model was the initial length of these q, k, and v vectors, and we'll do our computations in parallel for these parts. Okay, let's see how does that look like in code. In code, this ugly looking line does this thing for us. So this line will split the initial q, k, and v vectors. So initially the dimensions I want you to focus. Initially the dimensions of Q were batch size into sequence length into D model. Now after splitting, they will become batch size into sequence length into num heads into this decay. Cool. So I want to explain totally. I want to explain how this works. So I have added a comment. You can check out my repo, by the way. It's in the link, is in the description. Ended up implementing the entire transformer from scratch for understanding, and I'll seriously recommend you do the same as well. Okay. So what will view does? So this part of the code, what I've selected, this will split Q into H parts. Okay, number of heads is H. Okay, so we'll split in number of heads. Now we'll transpose it as well. What is this part doing? What actually this part is doing is, if you see the final dimensions, the final dimensions here before transpose, it is batch size into sequence length into heads into D. What I want, what I want is, I want num heads to be here and sequence length to be here, because so that once it is like this, once I've rearranged like this, now the model can treat each head independently during the attention calculation, right? So we can assume that we have this metric sequence length into self.dk this many times. Simple. So now this is independent and this can be treated in parallel. That is why I do this. So this ugly looking thing does the same thing. Now we have divided into parts and we have rearranged into how we want. Now we'll calculate attention patterns within each head. Now we'll time to use this formula. This is how attention pattern is described in paper. Q into K transpose upon dk. Dk is the length of every subpart, and then finally we take a softmax, convert into probability. Probabilities are assumed as weights, and then we take a weighted average of V to calculate updated values of V. That is how you. If you don't get it, if I ran it too fast, go and watch my previous video or read J. Elmer's blog. Very awesome blog. You'll understand about attention. Okay, let's keep our focus on implementation only. We'll go here. For this step, I have specially written a function scale.product. This function directly implements what is shown in this paper here. First step is take Q and K and do a matrix multiplication. Okay, easier said than done. Let's look into this function. Let's look at the function. First step, this line is basically doing a combination of this. Q into kt upon under root dk. To calculate dk, we have to do this. So this function does not take dk as a param. Why? Because it's fairly calculable from query, whatever query or key or value. The last dimension will be dk only. Right, so that is fairly obvious. So that's why we are not passing it as param. We calculate dk, and then this part is, believe me, this part is exactly similar as torch mat mul q dot transpose. I don't like this key dot transpose -2 -1. This is very unintuitive and very bug prone. So I introduce a lot of subtle bugs. If you can use it, if you can understand this, go for it. It's nothing different. So these two lines are fairly similar. This seems much more obvious to me, so that is why I use this. This is basically nothing but I'm doing a dot product after transpose. That's it. And then we are scaling it down by under root dk. So okay, so we have calculated this part qkt under root dk. Now we will take softmax. Simple. So let's see next step. Okay, so no, masking is also important. If we are in this masking layer, so there are, I said now we calculate three types of attention. So we already discussed how to differentiate between the cross attention and both of these self attention. Both of these self attention also differ. This one has a mask, this layer has a mask, and this doesn't. So we take it as a param. Do we want a mask or not? If we want a mask, we'll apply a mask here. Simple. If the mask is not none, if for in forward pass, we ask, do you want a mask or not? Let me show it to you. So when we call from encoder, we don't need any mask. So when we are calling from encoder, mask will always be none. In decoder, first layer will have mask. As you see in paper, we want mask in first layer and not in second layer. So let me just show it to you. In decoder, yeah, first layer will have mask. Actually, I'll tell you later why. It has target mask. What is the meaning of target mask? I'll come to you. I'll come back. Source mask. This is source mask. We send a mask here. Okay, and the source mask is sent here. So source mask is basically nothing but we don't want. Actually, no, sorry. This is target mask is important. Source mask comes in cross attention. My bad. We are talking about self attention right now. This is the first layer is self attention. Yeah, that is I got confused. Yeah, self attention requires target mask. Why? Because the model is trying to learn the relationship between target sequence and target sequence. So within itself, it is trying to learn the sequence. So we'll mask. I'll give you just a little intuition of why masking is important. Okay, this is the reason why masking is important. So when the decoder is in training mode, in the training mode, decoder is fed all the tokens at once. Right? In the training mode, we are doing teacher forcing. All the tokens are fed it at once, and all the processing is done in parallel. But in inference mode, that is not the case. In inference mode, decoder outputs one token at a time. For example, if in the inference mode, decoder will output one token, I'll take that and feed it again. Then decoder will output next token. Then I'll feed those two again. Then decoder will output third token. Then I'll feed it again. So if the sentence is eight tokens long, I'll have to take 8 times. The decoder will have to output it 8 times. The cycle will go on for 8 times, right? But that is not the case during training. So during training, when decoder is learning that to predict the next word is chasing, decoder has access to these two words also, a criminal on the run. But we don't want the decoder to look at these words, because during inference time decoder will not have access to these runs, these tokens. So that is why we mask them. We just say that in the attention pattern, when you're calculating the attention pattern here, when you're trying to calculate basically this matrix, this attention pattern matrix, I will not let you see what is. So this is cross attention, that is why you can see. So how will the mask look like? I think I have a picture here somewhere. Yeah. So that matrix will look like this. All this I will mark it to minus infinity. Simple. Why minus infinity? Because when I will take the softmax, they will become 0. Right. So that is why we need masking. Because one liner answer is because the behavior of decoder is different in training and different in inference. So we'll apply the mask. Where is my multi? Yeah, this is. We'll apply the mask, then we'll move forward. Then we'll take a softmax as seen in this diagram. Where is this diagram? Go to the paper. Yeah, then we take softmax. Once we have softmax, now we'll simply take the weighted average of all the V's. Sorry, one more detail. We'll add dropout as well, regularization. So dropout, let's see, paper tells regularization section paper. Self-attention, regularization, yeah. So they're saying we apply dropout to the output layer sublayer, okay. Whatever sums of embeddings, okay. For base model, no. So they have written somewhere that within attention also they apply dropout. I don't remember where they have written, but it is written in this paper somewhere. So this is where we apply dropout. Once we have calculated attention weights, we'll apply dropout to all the attention weights. Then we'll do perform the last step. Last step is to this. This is the last step. Softmax matmul this thing with V. That is what we'll do. Cool, we have done it. Again, this is just another way of torch.matmul. If you do torch.matmul attention weights or value, it will work exactly the same. Now we have attention. Now we have the refined embeddings of V. We'll return back to our main function forward. Here now we have attention weights and the output. What we'll do is now we'll concatenate all of them. This is just we are concatenating the results of all the heads. By the way, here we'll get the output from all the heads. So if you look at these vectors, I am always calculating in the number of heads. So calculation are being done for all the heads at the same time. Parallelism. So the parallelism comes in two places in transformer. Very important. One is we are processing all the words in the sequence at the same time, and then we are processing multiple batches at the same time. You see these batch dimensions, right? So we'll concatenate them. How we'll do that? Like this is what it says. All the we concat all the outputs, whatever we get, and then we add a linear layer. Concat here, we add a linear layer, and we are done. Why does this linear layer exists? In this current implementation, there is no. If you see this linear out, it has same dimensions. Self dv cross h d model, as I already told, dv is nothing but dk. So I think this exists because to add generalizability in this code. So if let's say dv is not equal to dk, and if dk star h is not equal to d model, then this linear layer, what it will do is it will rescale the whatever is the length of this right now. When we concatenate, the length becomes already equal to d model. But if it was not so, I think the linear layer will just scale it to whatever length you want. So you see there is no activation, it's just a linear layer, adds nothing, no non-linearity, just a linear layer. So I think this is to preserve generalizability. So in transformer we keep every output of every layer is 512 so that residual connections can be made. I think that is why we need a linear layer. So that's pretty much it, and we have implemented attention. See you guys in the next video. In the next video, what I'll try to do is I'll try to go over the entire implementation, decoder, encoder, and the transformer. But till then, that is it. See you, folks.